Brandon gave me a very good segue. Good morning. He talked a little bit about analytics. I'm going to tell you about a project we did at Jost that allowed us to leverage some new technologies to make a beneficial project for us to collect more data and to bring us into the 20th century with our manufacturing intelligence system. This was based around a historian. My name is Rick Tissier, as Janice said. I'm a lead controls engineer for Jost Chemical Company. Jost is a manufacturer of high purity inorganic salts. We're FDA registered. We are now in 4 buildings, over 350,000 square feet. We were founded in 1985 by Jerry Jost. We're now over 220 employees. We're a 24/7 operation. We produce and fully test much more than 7 billion kilograms a year of product in St. Louis. We're a worldwide sales and distributor organization. Our project team was Rockwell Automation. We utilized the Plant PAX distributed control system that Rockwell has. We also utilized a local Rockwell system integrator, McHenry Automation. Mike is here on the panel today. They were the technical lead for us to develop the system architecture, the network design that we used, the server implementation, and EMI report and screen templates. Jost chemical staff then implemented the system changes by the design and specifications provided by Rockwell and McHenry. I'm going to talk about the initial challenge we had at Jost, what the design was that we came up with, how we implemented that, some results and some lessons learned. Hopefully you can take some information back to your companies that will help justify projects. I know sometimes it's hard to get expenditures for these kind of things. Jost, our initial challenge, we've been a growing company. I've been there 7 years. We've gone from under $20 million in revenue to well over $60 million in revenue. We do all of our own construction in-house. We do our own engineering, our project engineering, all of our own building. We do, from a controls engineering standpoint, we do our own programming and everything to put it on the plant floor and make things work. Some of the issues we had multiple control platforms in use. Our process network was very flat, one server, no segmentation. And as a result of that, we had isolated process areas we couldn't get data from. The existing historian we had was very insufficient for what we needed for the whole plant and for our growth. We had custom and inconsistent PLC and HMI code. I'll talk a little bit about that later. And we had very inconsistent operator interface graphics, and I'll tell you why that was a little important to us. The key items we want to deliver with this project was a connected enterprise. We have a separate production network from our business network, like most people do. And we needed to make data from all of our production areas available on the workstations for the process engineers and the production supervisors. We also needed to standardize operator interface graphics. We're a very flexible company even in how we operate. It's not unusual for us to have an operator running one line one day and move to another line the next day and another one the day after that. Previous to this project, all those lines had different operator interfaces, so an operator had a mountain of training to go through to be able to switch lines. By standardizing the operator graphics, it made it much easier for him to make that transition. We also had to create an infrastructure that would sustain our anticipated growth. We don't plan on slowing down our growth anytime in the future. So the requirements we needed is we needed to implement this over at least a year or more and reuse existing investment that we had in software and network infrastructure. We needed to implement our EMI system early in the project so that we could realize some of the benefits that the manufacturing intelligence would give us. We knew there were benefits there. We couldn't necessarily quantify them, but we wanted to gain them as soon as we could. Our system had to be scalable and flexible. It needed to allow for the growth in the future and easy integration of future process areas, including some that were added during the project. It needed to provide cost savings, obviously have an ROI for the project, but we also wanted to implement efficient tools that we could use to create new processes in the future. And we needed increased reliability and security that we didn't have with our existing network structure. This is just a little graphic that shows one of our chemical processing tanks. And what I'd like you to see is there's an agitator on this that mixes the tank. If you know what you're looking at, there's a control valve there. There's a couple of transmitters there that give us temperature and level. The variable speed drives on the wall control the tanks, agitators that we have. So all these things the operator needed to control from his graphics. We selected the Rockwell Automation Plant PAX system that included distributed HMI and operator interface applications. And again, they were standard. That was a big thing for us. We collect data from all the process areas through our process historian, also through batch and event databases. We needed to have enterprise operating intelligence system that could be shared for analysis and reports on the production network or on the business network desktops. We needed processing graphics available on remote devices. We needed our production engineers and our process managers to be able to see what the processes were doing in real time, to see the same displays that the operators were seeing, so they could communicate effectively with them. And we also have a batch control system that went in from a third-party vendor, so we need to integrate that into our system also. Our system design, we revamped, we put servers in 2 buildings for increased reliability. We created some virtual process control networks. Flat architecture, we were just running out of bandwidth. So we have now one VLAN that serves the servers and the HMI and the controllers in our system. We have a second control level VLAN that lets the controllers talk to the I/O devices. There's just quite a bit of traffic from our variable frequency drives, and we're keeping that isolated now on the VLANs. We added additional switches and things for the process lane segmentation. Here's a diagram of our network as our design came out. We have a business network that sits on top. They control a firewall that we have revamped in the process. The 2 sides of that diagram represent the 2 buildings we have with 2 virtual servers in each building. Virtual servers obviously communicate on supervisory controls network to PLCs and HMIs, and there are multiple, more than a half a dozen in each of the buildings of PLCs. And those PLCs then talk to the controls network to pull I/O and variable frequency drive information. We had a lot of need for the information we could get off drives through communications, but didn't have a network robust enough to supply that information continuously to us. One of the big benefits that we wanted to see, and we found that in the plant PAX system, was the object libraries. This significantly reduced implementation time for our controls engineers. For the new processes that we built, as I said, we had 3 of them under construction as this project went in. We're also daily getting requests from the process engineers to convert processes and for new information. We gave us consistent operator interface graphics. I'm going to show you some graphics a little bit later on that demonstrates that. Programming was implemented by Jost and McHenry Automation, and the OEM equipment provider has the same look and feel of what our systems do, and they integrate it very easily. The virtual servers that we set them up with replication. We actually use Microsoft Hyper-V. We found, first off, that we had quite a bit of savings from using virtual servers over hardware boxes, obviously, and the Microsoft licensing policy allowed us to have a couple of virtual servers on each host that saved us some money in operating system software. This also greatly increased our reliability and reduced our server maintenance. We had a single managed connection between the process and business lanes. That was our new firewall that we implemented. One of the things we needed to do to implement was to use the EMI system early in the project to provide quick ROI for it. So we instituted the network modifications immediately as the first step. So we put the servers in, we built the virtual servers, and got the bandwidth we needed. We added more data points from more process areas. It just took a little cabling to bring them in once we had the capacity on the network system. And then our system integrator, McHenry, created templates for our EMI system for reports and remote graphics. We're using Factory Talk Vantage Point for the reporting system. Our owner very much feels that he wants the expertise in-house to do these kind of things. So McHenry partnered with us to teach us and to build reports and teach us how to build reports. Whereas our process engineers come to us with more needs in the future, we can develop them for them. And we have Henry for a backup when we get a little overburdened or out of our expertise level. So in addition, we also had them set up graphics that we could work through Factory Talk Viewpoint to our production manager's desktops. So we've created additional EMI reports and screens as needed, and that's an ongoing thing for us now. And we've started to convert existing process to new standard format, one area at a time. I talked a little bit about operator interface and how the operators had such a difficult time training. My problem child process in the plant was built before I got there. It's gone through about 3 integrators and about 3 other engineers on site that have worked on it. So it has just a multitude of flavors of logic programming and HMI interfaces. It has over 25 faceplates built on one HMI system, and the operators have to know what each one of them does. And several of them do some of the same functionality, but in a different way. So it's just very confusing and very hard to train people on. Our controls engineers were there almost constantly working with the operators, new operators, to help them understand what's going on. New process equipment that was programmed by the OEM. We had a manufacturer put in a big dryer system for us. They had their own controls built for that locally. We asked them to build that in the factory talk system for us. They did a great job on it, and it plugged right into our process seamlessly. We were up and running with that from a control standpoint in a matter of a couple of weeks. So that was very nice. Here's a little diagram to show you what the power of the operational graphics are, and this is what we've standardized on. Really, the only thing that our Jost controls engineers had to kind of design was the tank graphic. You see on the tank that there's a temperature level off to the side, there's an agitator in the middle, there's a couple of water valves or a couple of valves up on top. As an instance there for the water feed valve, we use touch screens, so an operator touches that water valve on the display and it brings up the faceplate on the left, which again is a standard faceplate. The operator sees a start or an open and close button. He also has a button there for interlock system. This particular valve has several interlocks on it. When he touches that button, if he has an interlock that's keeping that valve from opening, it'll be red and flash up at him right away. He touches that button, he goes to an interlock faceplate that shows him exactly what those interlocks are and which are satisfied and which are not. So it's very intuitive for the operators to be able to tell how to operate their process and what is abnormal in that process. This is an example of that same valve control in the logic programming. In the past, my problem child line had just all kinds of programming just to operate a valve. We probably had 4 different flavors of that. Here, our controls engineers grabs a control block for a valve control, drops it on the screen. He grabs a control block for an interlock, drops it on the screen. As part of our process, we already have our tag databases defined for the field instrumentation. He just grabs tags, ties them to that, and he's done. Implementing a valve like this is about an hour to a 2-hour effort for a controls engineer. So inherent in that is quite a bit of cost savings in the engineering effort. Some of the results that we had from our project with cost savings, use of Hyper-V I talked about a little bit earlier, reduced the number of licenses we needed, the virtual machines themselves reduced the number of hardware boxes we needed, and we saved well over $10,000 in the implementation because of that. Use of object libraries, we talked about some of the efficiencies in that from a control engineering standpoint. We estimated we saved well over $10,000 in the 3 process areas that we were constructing at the time. We have 3 new process areas under construction right now. I believe we'll save a little more money than that because we're kind of up on the learning curve now how to use this software. The operational improvements that we have, process engineers are continuously coming to us looking at the historian data and EMI system and suggesting process improvements and requesting additional automation. Standardized with the programming and library objects, they've really simplified the implementation of these suggestions. We actually have one process engineer now that wants some additional heating controls on 3 of his tanks. Once we have the field wiring in, we estimate it's going to take us about 4 hours to program 3 tanks for the heating controls. Just a tremendous savings in engineering costs. The increased automation has resulted in higher productivity by reducing batch times and operator errors, and I'll give you a couple examples of that in a moment. And obviously, I've harped on it, operators require much less training on the graphics. We train them one time and they have that, they can go. We actually have a trainer in the plant now, and part of the initial training for our operators is to show them the operator HMI system and what things mean. So by the time they get to the lines, they already know how to handle a lot of it. Some of the operational improvements that we've made, we basically take a mild acid, a mild base, and we precipitate salt. It's in a slurry. We have to dewater that, and we oftentimes do that by centrifuging. In one particular process line, we reduced the cycle time by 10% by being able to hit an endpoint much faster, and we've increased decreased the centrifuge time. That's added 1,600 pounds a day in product produced and out the door, so that's revenue on our bottom line. We monitor, we've actually grown enough that we've outgrown our utilities power supply to our buildings. We're in the middle of building a big substation now, but in the meantime, we've had just a struggle with trying to schedule production around so we don't overload our electrical supply system. So we've used our manufacturing intelligence system to watch the power systems, power supplies into the plant and our usages so we can schedule production around that. We've actually moved some production to the night shifts to try and save on demand costs. And we're also using some of Rockwell's sequencing routines now to start reducing batch times. This is just a little example of what our process engineers get. It has to do with our milling systems, but they have a graphic that pops up which gives them the data from the day before as to how much uptime they had on milling. We have kind of a combination of milling and packaging. There are entry-level employees that work that. In the past, we weren't a 24/7 operation. We are now, so there was a challenge for us to keep those people engaged and make sure they were working all night while they're here. So this is now that they know they know what's going on. I mean, it's improved the results. This is a graphic that goes with that milling that our process engineers can look at that uptime. They can look at this graphic, and they have a visual representation when the machines were on and off. Not only that, they also see a level in the graphs of the parameters, of the running parameters of the milling system to tell whether they were running at the right levels to provide a quality, consistent milled product. We also, it was interesting, I talked a little bit about the guys working on the night shifts, but they started a little competition out there, and they're carrying a graph of how much volume each operator packages and bills, and it's actually started a competition between the operators, kind of neat. Some of the operational improvements that were suggested by the process engineers, the improvements that we did in the milling, and that was mostly from a more of an on-stream time, resulted in about 6% additional milling. While that isn't bottom line, we're very strapped on milling capacity, and that added 900 pounds a day of milling capacity in that one mill. We have 6 of them running, so you can see that's quite a bit more capacity. Optimization of some other drying processes. Reduced drying times by 10%. Those particular processes are a long dry. That added 300 pounds per day per dryer to capacity. We've got 3 of those dryers, so it's 1,000 pounds a day more finished product out the door. Analysis of our process data allowed identification of some operating conditions causing quality issues in some of the milling. We estimated we were somewhere around 50,000 pounds a year that the quality was going bad. The analysis using manufacturing intelligence identified what parameters were getting out of spec that caused that. We instituted practices to not run outside those parameters, and we've not had any more rework due to that particular quality issue since then. Some of the lessons we've learned, we had a pretty close relationship with our IT department. We really didn't talk too much about hardware switches, network switches before we started the project. So we have several flavors of switches. They're all Cisco's, but they're just a little bit different in managing them. And for our controls engineers, it just makes things a little more difficult. In hindsight, I think we would have gone through and specified and studied a little bit, specified switches before we started the project. We obviously had to discuss the ownership of the VLAN, whether the IT people would handle our production VLANs or whether we would. We won out on that one. We produced detailed network documentation with McHenry's help before we started the project, and I would say if you're embarking on a virtual LAN project, that's an absolute must. We also created a documented backup and recovery plan for virtual images before implementation. Shortly after we had this project almost fully implemented, we had a crisis event, I guess you would say, on our business network that brought it to its knees for probably 2 weeks. We were able to ride out with our virtual production network, get machines back up within a matter of hours, and continue production without any disruption. After that experience, we saw our IT folks are starting down the road of virtualizing their LANs too. So that's all I have. We'll entertain questions. Thank you for your time. I appreciate it.